We have developed a method that increases the speed, stability, and precision of a control system by an order of magnitude compared to today's leading technologies. As you will see in the video, the impact of this method is meaningful enough to be observable to the naked eye, but is even more impressive when measured with a high degree of precision. We will demonstrate the method using a very simple magnetic levitation control system, but the applications are significantly broader. In general, systems react faster when the gain is increased. However, a gain increase to a high enough extent in certain systems can lead to oscillatory behavior and instability. With this algorithm, we get improved time response when we increase the gain while maintaining stability and robustness.
This new algorithm takes advantage of new sensors which are much more precise, have higher resolution, higher bandwidth, as well as digital signal processing units which work much faster. Our compensator is shown here in this diagram. We invert the invertible parts of the compensator and add some corrections, as well as 3 filters. J1 acts on low frequencies and J3 acts on high frequencies. And those 2 filters guarantee the realizability, the stability, the robustness of the system, while G2 of S acts mainly on the time response, reducing the settling time and the rise time, without affecting really robustness margins. That's the strength of the algorithm as it is now.
So to test our magnetic levitation device, we have a diagram here that describes the components of the system, and mostly what we want to do is to levitate this spherical metallic ball here with using an electromagnet that will lift the ball as we're putting current through it. So what we have here is the magnetic levitation device, and the ball is magnetically levitated right now, and it's under the control of a PID controller, which is proportional integral derivative. What we see is that the ball is steady at a position, and then we change the set point so that the ball can move up a notch by about 1 millimeter, as we see here. The response time is not great, and there is a little bit of overshoot, which is something that we will correct with the new controller.
We apply now a new control algorithm on the levitation system, and we're going to give some step inputs and check how the ball is reacting on the vertical plane. And as you can see, there's almost no oscillation when we go from one step to the other. If we look at the time response and zoom on it, we can see that there's almost no overshoot, no static error, and in less than 60 milliseconds we get a nice response. Note also that the rise time and the settling time are equal. If we do compare our compensator to a PID compensator, which has been optimized after many trials, we observe the following. Number one, the overshoot is quite important. Static error is small, but the settling time is quite big, 650 milliseconds. Therefore, our compensator performs much better. To validate qualitatively the robustness of the system, we're going to hang different objects, different shapes, different weights, and check the result without modifying the compensator. This is the result. The algorithm can be applied to any system, and we apply it to a hard disk. What we would like to do is control the arm of the hard disk and make it vary from one position to another the faster possible. So we take our hard disk model, apply our algorithm, and compare the solution to the other solutions that do exist. as you can see here, with PID we get 63 milliseconds. With H-Infinity 1.5 milliseconds, with H-Infinity control. With algorithm we get 0.27 milliseconds. In fact, comparing simulation with simulation, we see that our algorithm is much more interesting.
For more information on this patented technology, please contact either Aligo, a company specialized in the marketing of university inventions, or directly to the research professors, David Bensoussan and Benoit Boulet.